Hello everyone, welcome back to the course on measurement and instrumentation, and this is our 6th week of discussion and we are talking about analog meters, okay, and this is the 3rd lecture of our 6th week, okay. Today we are going to learn about how to measure high resistances. We started with the resistance measurement and we first discussed about measurement of medium resistances and then we discussed about low resistances, okay, and now we are talking about a high resistance. And in the initial class we have actually discussed about this spectra of, I would say, resistance, where we talked like anything greater than 100 kilo ohm or say 0.1 mega ohm, we have classified them under high resistance, okay. So, before we actually jump into the measurement techniques for high resistance, let us try to understand what could be the difficulties in the measurement of high resistance. For the low resistance measurement, we have seen that the connecting probe, if you remember the Wheatstone bridge configuration, we have seen that the lead that is connecting between the resistance S and the R was a major problem, and to avoid that, what we have done is we have used a Kelvin double bridge kind of arrangement, right. In the Kelvin double bridge arrangement, we have used some inner ratio or inner arms where we have kept the ratio of small p by small q and we have equated with the ratio arms, which was the capital P by capital Q, right. So, this was our low resistance measurement technique, and we started again the low resistance measurement with the difficulty in measuring in the low resistance, and we have seen an example that how the contact resistance plays a significant role when you discuss when you try to measure actually low resistances, okay. Similarly, let us try to understand the difficulty in measurement of high resistance, okay. So, in the resistance which is under measurement, say for example is of very high value, very small currents are encountered in the measurement circuit, okay. So, I have a resistance say R, okay, and I have applied say voltage V, okay, and now say this is I am calling a case 1, okay, and I have another case where the same voltage source is used, okay, and say of course, we have to see it in broader perspective where we have used say for the medium resistance measurement say ammeter voltmeter methodology or any other method, but I am giving you a simpler view, okay, and say this is case 2 where the same battery is connected. However, this resistance is now 10 power 6 R, all right, and say this is current I1 in case of case 1 and say this is I2 in the case of say second case, all right. So, this I1 is equal to V by R, okay, and I2 is equal to V by 10 power 6 R. So, the second case is actually the high resistance case, right. So, this is the high resistance case. Now, if I want to check the ratio of I1 and I2, okay, so this will be equal to say V by R into 10 power 6 R by V, okay, if I cancel them, okay. So, I could say that this I1 is basically 10 power 6 times the current I2, or in other word, I can say that this I2 is I1 divided by 10 power 6, okay. Means this I2, if I am increasing the resistance or if I am trying to measure a high resistance, okay, and if I am using even the same voltage source, my current value will go down significantly. Now, say if now in case 2, say if I am using say 100 times the voltage source that I was using, okay, with EMF 100 times, okay. Now, I have this 10 power 2, okay. Now, in this case also I2 is I1 divided by 10 power 4, all right. So, it is still 1 by 10,000th of I2. Now, if I increase this voltage to be say 1000 volt, Okay. Now, this I2 value is I1 divided by 10 power 3. So, 1 by 1000 time of the current I1, which is also very, very small. So, even I have increased the potential. Of course, in practical sense you can say if it was say 10 volt and now I am making it 10,000 volt. Okay. Very difficult to measure, but still I am making it say 10,000 volt. Okay. Now, then also the current values have not gone very high. It is still very, very low. Okay. So, very small currents are encountered in the measurement circuit when you try to measure very high resistance. Okay. So, whatever I am talking is in practical sense only. Sometimes we have to measure resistances of this order, particularly if you are trying to measure say resistance of say insulating materials like dielectric materials. Okay, like if you are trying to measure resistances of certain cables which are very high resistance, transformers. Okay, sometime in electronics also, particularly in the semiconductor devices, but when you talk about say reverse bias junctions. Okay, you may encounter very high resistances. Okay, and this is not something which is not practical. This is very practical, and we have to come up with a certain method by which we can measure this kind of high voltages. Okay. Now, when you try to measure the high resistance, there are several challenges. Okay. And one of the severe challenges that you face while measuring the high resistance is the leakage current. Okay. Now, leakage current are of comparable magnitude to the current which is being measured, and therefore has to be eliminated during the measurement. Okay. Then we will talk about the leakage current in little detail also, that how to avoid it, but then let us see that what can be the other challenges while measuring the high resistance. Okay. Then in this kind of resistances, electrostatic effect has very strong influence. Okay. And due to the electrostatic effects, stray charges can appear in the measuring circuit, which can again cause different errors. Okay. Now, in the measurement of insulating resistances, the specimen's capacitance also you have to take into consideration. So, only resistance if you try to take, okay, you may be eliminating significant amount of actual resistance. Okay. So, therefore, the capacitance, because these are dielectric materials, so the capacitance also comes into the picture. Okay. And while considering its resistance, you have to also consider fairly its resistance. Okay. So, usually very high voltages are used in test in order to raise the current to reasonable values in order to be measured. One example we have just seen, okay, where I have increased the voltage from 10 volt to 10,000 volt, even then also my current which I was trying to measure has not gone beyond 1 by 1000 times of the actual value. Okay. So, if you have to measure, or if you are applying such a high voltages, okay, or when you have this much small current flowing, you should normally have a sensitive galvanometer or micro ammeter for this kind of measurement. Okay. And you also have to take adequate steps, to prevent damage of this delicate instrument, because they are sensitive, but when you end up flowing large current, they may get damaged immediately. Okay. So, I mean, these are certain challenges that we face while measuring the high resistances, but the major challenge that we actually face is the first one that we have seen, that is the high leakage current in this kind of measurement. Okay. And to eliminate that, or to eliminate the leakage current, or at least to minimize, a guard circuit is used. Okay. So, let us see what is a guard circuit and how it can eliminate errors caused by leakage current over the insulation. Okay. Now, try to understand this with certain example. Okay. So, usually the conductors which are under measurement, okay, have some cladding. Okay. They have a certain cladding, okay, on top of it, to keep it insulated. We have also seen this in our homes also, that wires in our home have certain form of jackets, right. So, say this is the wire, and on top of this, say sometime it comes in red, black, and if it is say two different wires, okay, they will be entangled. Okay, so we have came across this kind of arrangements. Okay, now let's see that if I am trying to measure high resistance, for example, using the voltmeter ammeter method that we have seen earlier. Okay, now in this case, say high resistance which is under measurement, say this resistance R, okay, is mounted on a piece of insulating material, okay, and now we are trying to measure it. Okay, so if it is not mounted on piece of insulating material, you take into consideration this jacket which is wrapped over this insulator. Okay, now the microammeter which is placed over here, okay, this measures the sum of current through the resistor IR, okay, and the current through the leakage path around the resistor. Okay, so this IR that is flowing through the resistor, okay, plus the leakage resistance, okay, which is there in the, say, through this outer jacket, for example, okay, that is there, and the ammeter is basically, say, if current I is flowing through this, means this I has distributed like IL and IR. So this I is equal to IR plus IL, means that this micro ammeter is basically measuring not the IR value. Okay, ideally it should measure IR. If I want to calculate this unknown resistance, then only I can say that it is V by IR. However, in place of measuring IR, what it is measuring is the resistance which also include the, or current which also include the leakage current. Fine. Now this microammeter measures these two different currents. Okay. Now the measured value of the resistance computed from the reading indicated on the voltmeter and the microammeter will not be the true value, because the ammeter reading is wrong. Okay, and therefore it will be erroneous in nature. Okay, now what we do is we have now introduced a guard circuit. Okay, now say this is the guard terminal. Okay, this has been added to the resistance terminal block. Okay, now the guard terminal surrounds the resistance terminal and is connected to the battery side of the microammeter. So the battery side is, this is the battery side. So now this is connected somewhere here. Okay, so this is connected to the battery side of the ammeter, and this connection configuration is very, very important. Okay, now when you have this kind of arrangement, the leakage current IL, okay, which was flowing like this, okay, is now actually getting bypassed at this point, where it bypasses the microammeter and now it moves like, it flows like this. All right. So now whatever current this microammeter is measuring is actually, or at least very near to the current value which it would have been measuring earlier when there was no leakage. Means that this current which is measured by this ammeter or microammeter is equal to the current which is flowing in the load resistance or the high resistance which is under measurement. Okay. Now this allows the correct determination of the resistance value from the reading of the voltmeter and microammeter configuration. Okay. So using this guard circuit, you are now able to measure the actual value of the resistance by calculating the voltage and the current flowing in the voltmeter and ammeter respectively. Okay. So this is concept of guard circuit, and we will be using it regularly in this class. Okay. So there are different ways or methods which have been employed for measurement of high resistances. Okay. And this include generic method of measurement like direct deflection method. We have also a very important method, that is loss of charge method. Okay. Then there are other methodologies like megometer method, guard ring method, and so on. Okay. Let's discuss some of these methods so that we know that how to measure these high resistances. Okay. Let's first talk about the direct deflection method. Okay. So the direct deflection method is basically this configuration. Okay. And please recall this kind of configuration. If you remember, from the previous slides, we have discussed this configuration when we actually introduced the guard terminal. Okay, so this guard terminal configuration is basically direct deflection method, okay, for measuring high resistances. Okay, so for high resistances such as this insulation resistance of cables and say reverse bias of the semiconductors, PN junctions and so on, you require a very sensitive galvanometer. Okay, because your current levels are very low. Okay, one of the example of the measurement of insulation resistance of a cable which is having say metal sheath, we all have seen this kind of cable where you have a conductor. Okay, on top of it you have a plastic cladding. Okay, so this looks like this, and on top of this you have another metal jacket. Okay, and sometime even on top of this you have another cover of plastic, right. So I am not considering this right now, only this three configuration. This is say metal, we are calling it metal sheath. Okay, then this insulating material or say jacket of this wire, okay, or the conductor. All right, jacket of the conductor. Okay, and you have this galvanometer and voltmeter connected like this. Okay, you can see this particular figure. Okay, now if you see very carefully, I have connected this galvanometer here with a conductor, while this I am calling a guard wire, and now this from the guard wire you have this this leakage current flowing. Okay, and please note that this guard wire, similar to what we have seen in the guard circuit, is wrapped on the insulating part of this wire and not on the metal sheath or on the conductor. Okay, now the galvanometer in this case measures the current IR which is between the conductor, between this conducting part of the wire and the metal sheath. So basically one electrode is this conductor and another electrode is this metal sheath, and in between you have this current IR flowing, which this galvanometer is basically measuring. Okay, now the leakage current IL over the insulating material is carried by the guard wire, which is wound on the insulating material, as you can see over here. Okay, so therefore it does not flow through the galvanometer. Now this leakage current is now bypassed by this kind of configuration. Okay, now the direct deflection method is used for the measurement of insulation resistance of insulating material sample, which is also in the sheet form. So this is what we have seen is one configuration, but then we have another configuration like this. Okay, where what you are trying to measure is the not the resistance, but what you are trying to measure is basically the volume resistivity and the surface resistivity of material. Okay, and you can see this part is the specimen. Okay, and this is your electrode D2 and this is the electrode D1. You can please note this edged part between this D1 and D2 are not equal. Okay, so D1 is not equal to D2. Fine. So in this kind of configuration, the leakage current over the edge of the specimen will flow between the guard ring, okay, and the lower electrode having this dimension D2. Okay, and hence will not introduce error into the measurement. All right. Now the volume resistivity rho can be given by the formula. We will see that, but before that let us see the different dimensions. This D1 is the diameter of the upper electrode. Okay, T is basically thickness of the specimen. Okay, V1 is the reading of voltmeter and I1 is the current that is flowing through the galvanometer 1. Okay. Now the resistance of the specimen that we are about to calculate can be given by simply by the voltage divided by the current value. Okay, so R is given by the voltmeter reading V1 by I1 when the galvanometer is in this connection. Okay, now the volume resistivity of the specimen can be given as rho equal to pi d1 square by T into R, where R was rho T by pi d1 square. Okay, I mean this is coming from the standard formula of the resistance. Okay, and the volume resistivity can be given as since R was V1 by I1, so the resistivity can be given, or volume resistivity can be given by pi d1 by t into V1 by I1. Please note that you are aware of all these parameters. Okay, so you already have the current flowing through this galvanometer, so this gives you I1. You had voltmeter reading V1, okay, D1 you have made this electrode, okay, T is the thickness of your specimen, and that's how you basically calculate the volume resistivity. Similarly, you can also calculate the surface resistivity, okay. Please note that the resistivity of thin layer of dielectric material is different from volume resistivity. It is not same as the volume resistivity, and this is because of different layers of, say, gases, humidity, surface contamination, chemical alteration, absorption of gases, etc. at the surface of the this specimen sheet. Okay. Now, the resistance say RT between the two electrodes attached to a dielectric medium is composed of volume resistance RV and the surface resistance RS. So, if you want to calculate the resistance RT, it can be given as the parallel configuration or parallel combination of the volume resistance and the surface resistance, and you can calculate it as 1 by RT which is equal to 1 by RV plus 1 by RS. Fine. Now, if we want to measure the surface resistivity, now galvanometer has to be placed in the configuration G2, not in the G1. Okay. Now, in this position, the galvanometer measures the leakage current now. Okay. Now, the current flowing between the upper and the lower electrode will be eliminated from the measurement in this configuration. Okay. Now, let us say D2 is the diameter of the lower electrode that we have seen, and V2 is the reading of the voltmeter, and I2 is the reading of the galvanometer when it is in the position G2. The surface resistance RS can be given as V2 by I2, and the leakage current flowing along the path of length, say T, which is the thickness of the specimen, and the width D2 with the surface resistivity rho s can be given as RS into pi D2 by T. So, if this is your surface resistivity, and RS we already know from the galvanometer connection as V2 by I2, you can easily find rho s in terms of the values of galvanometer and the voltmeter as pi D2 by T into V2 by I2. Okay. So, this is how you actually measure the volume and the surface resistivity of the insulating material, and of course, once you know this, you can also calculate the RS and RV. Okay. Now, this is just one way of measuring high resistance. You have another methods also, we have talked about that. Okay. So, another method which is very important for measurement of high resistance is, say, loss of charge method. Okay. So, as the name suggests, it is a method which uses or which rely upon charging and discharging of the capacitor. Okay. So, in this method, say the insulating resistance, say R in this case, okay, to be measured is connected in parallel with the capacitor C. Okay. This is the C, okay, and a electrostatic voltmeter. Okay. This is the voltmeter I am talking about. So, this is the voltmeter. All right. Now, the capacitor is charged to some suitable voltage by means of a battery V, okay, and is then allowed to discharge through the resistance. So, if I want to charge this capacitor, I have a switch over here. I will close this switch, okay, and say if this battery has EMF V, I will allow this capacitor to charge, okay, and if I want to have a discharge of this capacitor, I will open this switch S, okay. So, I can have two positions for this particular switch S. Okay. Now, the terminal voltage is observed over a long period during discharge. I mean, this long period of discharge is because this resistance is very, very high. Okay. So, the voltage across the capacitor at any instant of time, say t, after the application of voltage can be given as this small v equal to V into e power t by CR, or this voltage V can be given as this small v, which is the voltmeter reading, into e power minus t by RC. Alright, or this capital V by V is equal to e power minus t by RC. Okay. So, for insulating resistance, this resistance can be given as the time divided by the capacitance into log E V by V, And if I convert this into log 10, okay, if I will have this value as 0.4343 into time divided by C log 10 V by V. So now if I know the time, this V and V voltmeter reading and the capacitance reading, I can calculate the insulating resistance. Okay. Now the variation of the voltage V with time can be simply shown by this particular equation, where this V is varying like this. So this is V e power minus T by RC, right? Fine. So this capital V, which was the EMF battery, divided by this voltmeter reading, is equal to e power minus T by RC. And if the resistance R is very large, the time for a noticeable fall in the voltage will be even larger, because the resistance is very large. Okay, and this process will be time consuming, so it will take considerable amount of time for this discharge. Okay. Also, the voltage time curve will be very flat, and unless great care is taken in measurement of the voltage at the beginning and end of the time t, error may be made in the ratio of V by V, causing a considerable corresponding error in the measured value of the resistance. Okay. So what we can do to take care of that? Okay. So usually in practice, what we do is, we, in place of calculating the actual V, what we do is we calculate V minus small v, or the battery EMF minus the voltmeter reading. Okay, and say we call this value as E. Okay. Now this this R value can be from this equation. For example, say I am calling this equation 1. Okay, R was 0.4343 T by C log 10 V by V. Okay, now I am calling say V minus V as E. Okay, this capital V by small v as E. Okay, so I can say that this small v, which is the voltmeter reading, at any instant of time is V minus E. Alright, where E is the difference between, at any instant, the difference between the EMF value and the voltmeter value. Now, if I replace this V with this particular value, I can say that this R is equal to 0.4343 T divided by C log 10, okay, V by V minus E. Alright, like this. So this is my second equation. Okay. And this change in voltage can be measured by the galvanometer. Okay. So this E is not very difficult to measure, and once you have this measured value for the E, you can easily calculate the resistance, and therefore this loss of charge methods are very suitable for high resistance measurements. Okay, because although it seems to be time consuming, you can eliminate that time consumption part by taking the subtraction of these two voltages rather than waiting for the voltmeter to show you certain value. Okay, so they are suitable for high resistances. They have good accuracy, and they also have a minimal loading effect, but then limitation is still the time consumption that it takes. Okay, and then they are sensitive to leakage paths. To counter that, to counter particularly the leakage paths, okay, there are some configurations of this resistance capacitances in the circuit, okay, that has to be taken care, okay, which will at least reduce the leakage path. Okay, so we can have that kind of arrangement. Okay, therefore the loss of charge method is one of the very important or very crucial method for measurement of high resistances. Okay, so with this, I think we have finished our discussion on resistance measurement. If you are interested in learning some more techniques of say high resistance measurement or say low resistance measurement, I will suggest that you go through some standard textbooks. Okay, because of the time constraint, we are only covering these particular types, but even though if you know these methodologies, at least in the laboratory, it will not be difficult for you to measure high resistance or even the low resistances. Thank you.